Hi everybody, welcome to lecture 30 of Electrical Engineering 331. So we've finally made it to our last lecture, and as you can see, we're going to be doing still more review. In just one quick note, in lectures 28, 29, and now in 30, we have reviewed some problems from tests 1 through 11. And then I think, we're also covering some material related to more recent work we've done. But we have not reviewed everything, so be careful. Be sure to review the other daily tests as well. But I'm hoping that at least reviewing some of this older material will be helpful to you. So, example 30.1, the first example in this lecture, asks if it is possible that the response of an LTI system, let me start over. Is it possible that the response of an LTI system to the input x of t equals e to the minus 2t u of t is y of t equals e to the minus 3t u of t? If not, explain why. If so, what is the impulse response of this system? So let's think about this for a moment. Both of these signals here exist only for t greater than or equal to 0, and so we can take the Laplace transform of each of these signals, and so we can work in the Laplace domain. So let's do that, and we'll say h of s. Let me try to make this a little larger here. H of s is equal to y of s over x of s. Okay, well, if y of t is e to the minus 3t u of t, then y of s is 1 over s plus 3. And if x of t is e to the minus 2t u of t, then x of s is 1 over s plus 2. And so this would give us a transfer function of s plus 2 over s plus 3. And if you proceed to try to find the corresponding impulse response, which is simply the inverse of this Laplace transform, then you see that if you want to invert this Laplace transform, the first problem that you see is that the degree of the numerator is not strictly less than the degree of the denominator. In fact, the degrees are equal to each other. So we need to do division first, but this is a very simple division, and so we end up concluding that h of s, which is equal to s plus 2 over s plus 3, is the same as 1 minus 1 over s plus 3. And so the corresponding h of t is delta of t minus e to the minus 3t u of t. And certainly nothing looks wrong with that. So we conclude that, that this input-output pair is possible, and this is the corresponding impulse response for this system. And in fact, I looked at it for just a moment, and you can actually see that this circuit right here would have exactly this transfer function. This is a voltage divider, and so the transfer function will be the impedance of this, which is R plus 1 over C1S, which in this case then would be, since R is 1 and C1 is 1/2, it would be 1 plus 1 over 1/2 S. And so it would be that, and then the denominator would be this, with the impedance of this plus the impedance of this. So you have 1 for the resistor, 1 over C1S. Well, here's 1 over C2S, so that would be 1 over 1S and 1 over C. I'm sorry, this is this is C2 here, so 1 over 1s and 1 over 1/2 s for this one. And so then if you multiply, well, actually we can say 1 over 1/2 s is the same thing as 2 over s, and the same thing down here. And then we multiply top and bottom by s, and we get s plus 2 over s plus 3. So certainly, since we have been able to find a circuit like this, it makes it very clear that this is a perfectly acceptable input-output pair. Even though it may seem a little strange to you, it is perfectly acceptable. So let's come to another problem where we again will ask if a certain input-output pair is possible. This time we say, is it possible that the response of an LTI system to the input x of t equals cosine t is y of t equals cosine 2t? If not, explain why. If so, what is the impulse response of this system? Well, if you think about this for a moment, right away you might become suspicious. Because remember, if you have a system with input x of t equals cosine t, then you can use phasor analysis. And you know that the output will be a sinusoid of the same frequency. But here we're getting an output that's a sinusoid of a different frequency. So this doesn't look right. It doesn't look right at all because, again, this disagrees with everything we've done with phasors. So let's try to understand why it's not right. Okay, well, we know that, now first of all, let me point out that since these signals exist over all time, it's no longer appropriate to use Laplace transforms. Here we use Fourier transforms. So we have y of omega equals h of omega times x of omega. Now, for the cosine of 2t, the Fourier transform is pi times delta of omega minus 2 plus delta of omega plus 2. And then h of omega, we don't know what that is. That's what we're really trying to find out. But the x of omega, since x of t is cosine t, x of omega is pi times delta of omega minus 1 plus delta of omega plus 1. So if we cancel the pi's on each side and take into account that h of omega times delta of omega minus 1, this is our old principle that if we have a function multiplied by a delta function, then this multiplying function or coefficient function, we just evaluate it at the point where the argument of the delta function goes to 0. So h of omega times delta of omega minus 1 is the same thing as h of 1 times delta of omega minus 1. And h of omega times delta of omega plus 1 is the same thing as h of minus 1 times delta of omega plus 1. So if you look at this equation now, after we've done that and canceled the pi's, we get delta of omega minus 2 plus delta of omega plus 2 is h of 1 delta of omega minus 1 plus h of negative 1 delta of omega plus 1. And you can see this is just not possible because the left-hand side is equal to 0 everywhere except at omega equals plus minus 2. And the right-hand side is equal to 0 everywhere except for omega equals plus or minus 1. So there's no way that this equation can be true, and therefore this is not up here. This cosine of t is an input and cosine of 2t is an output. That is not a possible input-output pair for an LTI system. Okay. Now, for example, 30.3, suppose that the response of an LTI system to the input e to the minus 2t u of t is y of t equals e to the minus t minus e to the minus 2t u of t. What is the response y1 of t of this system to the input x1 of t equals e to the minus t u of t. Now, I hope you'll try this on your own first before looking at the solution I'm about to present here. Okay, so as usual, we can find the impulse response by taking the Laplace transform of this known output and divide it by the Laplace transform of the corresponding known input. So we have h of s is equal to y of s over x of s. The Laplace transform of this y of t here is 1 over s plus 1 minus 1 over s plus 2. And the Laplace transform of the corresponding input is 1 over s plus 2. And so if you get a common denominator here in the numerator, this is equal to 1 over s plus 1 times s plus 2. And then in the bottom, we just have 1 over s plus 2. And so after we do this division, we're just left with 1 over s plus 1. So that is the impulse response of this system. H of s is equal to 1 over s plus 1. Now to find the response to x1 of t equals e to the minus t u of t, well, we just take that h of s that we just found, which is 1 over s plus 1, and multiply it by the Laplace transform of this new input, which is e to the minus t u of t. And so the Laplace transform of that is 1 over s plus 1. And when we multiply them together, of course, we get 1 over s plus 1 squared. And we know that the inverse Laplace transform of that is t e to the minus t u of t. So that would be the response of this system to this input right here. And then we have one more question, and we're going to do this question in two different ways. And pay careful attention, because I think it's interesting to see everything here. And this is our last example in this lecture. So this is, if you look back, we were doing graphical convolution in lecture 11 and in test 11. And so let's evaluate the convolution of these two signals right here using graphical convolution, and then we'll use Laplace transforms to evaluate the convolution, and we will compare. Okay, well, for the graphical convolution technique, remember that we can write the convolution integral in two different ways, and that I recommended that you write it in the way that associates the more complicated argument with a simpler function. Now, to me, this function is simpler because it's equal to a constant. This one is not a constant, so I think this is the simpler function. And so down here, I chose this form for the convolution integral. This form associates the more complicated argument with the simpler function. Remember, the other option we could have chosen would have been integral negative infinity to infinity of h of tau x of t minus tau d tau. Then the more complicated argument would have been associated with this function, but I prefer to go this way. Okay, so once we've determined that we're going to associate that more complicated argument with h, then you might remember the first thing we do is we take our plot for h, which here is a function of t, and we're going to make it a function of tau, and we're also going to flip it to get h of negative tau. So we get this. When we flip it and make the variable here tau instead of t, and of course the flipping is reflected by that negative sign, then we get this. And so h of t minus tau will look like this. We just, remember, we add t to each of the endpoints. So this is 0, so that becomes t, and this is negative 1, so it becomes t minus 1. And then we don't know what t is, so we're going to put it over here to the left. It doesn't matter exactly where, we're just going to put it over here. The main thing is to put it far enough to the left so that it doesn't overlap with any part of x. Okay, and then x of tau, of course, there's not much to that. Here's x of t, and we just replace the t's by tau's, but otherwise everything stays the same. So you you put down x of tau, you put the graph of x of tau and the graph of h of t minus tau, put those two graphs top and bottom like that. It doesn't really matter too much which is top and which is bottom, although I prefer to put the h on the bottom. Or excuse me, I prefer to put on the bottom the one that is going to be moving as we change t. So in this case, that's h. And remember again, now this is the integral that we want to look at. So now we're ready to evaluate this integral. Okay, so this convolution is clearly, you can see it's clearly going to be equal to 0 if t is less than 0, because if t is less than 0, there's no overlap. So we have 0 if t is less than 0. Now, if t is between 0 and 1, which is the case we will consider next, then this integral becomes the integral of, now h is just equal to 1, and x, you can see that this, as long as we're between 0 and 1, x of tau is just equal to tau. So we have integral from 0 to t of 1 times tau d tau. Now, as t continues to increase, it will eventually pass 1, and at the moment when t passes 1, this trailing edge, t minus 1, will enter the range here, between 0 and 1. So the next case we look at is if t minus 1 is between 0 and 1. And then we want to integrate from this back edge to 1. So we have, that's what we have here, integral t minus 1, which is the back edge of this, to 1, which is here. And again, we're integrating 1 times tau, because h is equal to 1, x of tau is tau. And then finally, when t minus 1 passes 1, then there's no overlap, and so once again we will get 0 if t minus 1 is greater than 1. Okay, so now you know that when you integrate tau d tau, you just get tau squared over 2, and in the first case here we're integrating from 0 to t, and in the second case from t minus 1 to 1. And notice that for all of these limits, I've just brought them down. Oh, this one, I've added 1 all the way through, so it becomes 1 is less than t is less than 2. And likewise here, I've added 1 to both sides, so it becomes t greater than 2. And so then when I evaluate these terms that resulted from the integrals, I get this final expression for the convolution. So that's the answer that we obtain using the graphical technique for convolution. And now I want to do this in a completely different way, and that is with Laplace transforms. And I really strongly recommend that you look at this very closely, because it really, in some cases, is a very attractive alternative. Now, I'll tell you personally, for this problem, when I worked it, I found this to be a little more tedious than the graphical technique. But you may not agree. But certainly there are some problems where the Laplace transform method is easier than the graphical technique. So I think that's a matter of personal choice. And one of the nice things about the well, I think I'll leave that off. I think I'll just say so anyway, it's good for you to be familiar with both of these methods, and I think you will find that in some problems you think one way is better, and in other problems you will think another way is better. But let's see how this Laplace transform method would go. Okay, so I'm going to call this this convolution, I'm just going to give it a name so that I don't have to always write h of t convolved with x of t. I'll just call it y of t. And so Laplace transform theory tells us that if we take the Laplace transform of both sides of that equation, on the left-hand side we'll get y of s, and on the right-hand side we get the Laplace transform of the convolution, which is just the product of the individual Laplace transforms. And so we get h of s times x of s. Now, in order to find out what these Laplace transforms are, we really need formulas for h and x, but that's pretty easy. We come back up here and look at h and x, and you can see pretty easily that h is equal to u of t minus u of t minus 1, and x of t is r of t minus r of t minus 1 to make it flatten out, minus u of t minus 1. So we'll come back down here and substitute those formulas for h of t and x of t. U of t minus u of t minus 1, that's h of t. R of t minus r of t minus 1 minus u of t minus 1 is x of t. And now we take the Laplace transforms of both of those. And these are in your tables, and what we get is these expressions right here. And so over here we already have a common denominator. We can just put everything over one denominator, 1 minus e to the minus s over s. But over here, notice that we don't have a common denominator yet. We can get a common denominator if we multiply this numerator by s. And so once we do that and then put everything together, we have 1 minus e to the minus s minus s e to the minus s over s squared. And then when we multiply these by each other, multiply them together, we will get this. And notice that the denominator becomes s cubed. Now, what I've done in going from this line to the next line is just I have looked, and I see I have two terms here that have s as a coefficient there and there. And so I know that when I divide those terms by s cubed, I'm going to get an s squared. On the other hand, for all the other terms, they have no s coefficients, so they're going to be over s cubed. So I'm going to separate the terms into the terms that don't have s as a coefficient and the terms that do. So the terms that don't have s, now notice there's one other thing I can do here. Okay, I'll bring down to 1, but this e to the minus s here, minus e to the minus s and minus e to the minus s here become minus 2e to the minus s. And then I also have an e to the minus 2s there. And then this minus s e to the minus s is there, and s e to the minus 2s is there. And all of that is over s cubed. And now I break up each individual term, so I get 1 over s cubed minus 2e to the minus s over s cubed plus e to the minus 2s over s cubed. And then, as I said, now for these two terms, we're going to get s squared in the bottom, so I get minus e to the minus s over s squared and plus e to the minus 2s over s squared. Okay. Now, we are ready now to take the inverse Laplace transform. Now, you may not recognize this one, but it is in your table. It's entry 5 in table 3-2, page 97. And the inverse Laplace transform of this is 1/2 t squared u of t. Now, this one is similar. We have 1 over s cubed again, but since we have a 2 there, there will no longer be a half. And since we have e to the minus s, that makes it t minus 1 squared and u of t minus 1. So we have, and then of course we have the minus sign. So this is minus t minus 1 squared u of t minus 1. Now here, again, this is like that term. And again, the coefficient is 1, so we're going to have the 1/2 popping in again, as we have over here. We're going to get 1/2 right there. And we will again have t squared u of t, but because of the e minus 2s, that becomes t minus 2 squared u of t minus 2. And so that's what we get there. And then e to the minus s over s squared becomes r of t minus 1, and e to the minus 2s over s squared becomes r of t minus 2. Okay? Now, what I will do next is I'm going to rearrange these terms so that they are in, I guess you might say, sort of increasing size of the shift in the u function, or the shift of the function. Let's just say it like that. See here we have no shift at all. It's just t. And then here we have u of t minus 1, so we have a shift of 1. Here we have a shift of 2, but here we're back to a shift of 1, and here we're a shift of 2. So I'm going to group together all the terms with no shift, which is only the first one, and then all the terms with a shift of 1, which are these two, and then all the terms with a shift of 2, which is these two. Now remember that r of t is the same thing as t times u of t. So everywhere I have an r term, I can substitute that. So I get 1/2 t squared u of t for that, minus t minus 1 squared u of t minus 1 there. But then this r of t minus 1 becomes t minus 1 times u of t minus 1. And then this r of t minus 2 there becomes t minus 2 u of t minus 2. Okay, so we're almost done now. This just comes down. When I take this negative sign inside and square this term, I'll get minus t squared plus 2t minus 1. But then I also have this multiplying u of t minus, see, this is multiplying u of t minus 1, but so is this one, so I'll get a minus t and a plus 1. And all of that is multiplying u of t minus 1. And then similarly, I'll group together the terms multiplying u of t minus 2, which are these two terms. And so when I square this, I get t squared minus 4t plus 4, but then I have to divide that by 2, so I get t squared over 2 minus 2t plus 2. And then here I just get a t minus 2. And now we simplify all these expressions. This just comes down. There's no more simplification that can be done there. Here the plus 2t and minus t become t. Minus 1 and 1 cancel, so we have minus t squared plus t. And here the 2 and the negative 2 cancel. The t squared over 2 comes down, and the negative 2t and t just becomes negative t. And so now, since we have simplified as much as possible, now we're ready to put this in a form that will allow us to compare with our previous answer. And you can see, okay, this term turns on at t equals 0. And what I mean is it's equal to 0 if t is less than 0, but then if we increase t beyond 0, it becomes non-zero. And similarly, this one turns on at t equals 1, this one turns on at t equals 2. So if t is less than 0, all of them are off and we get 0. So it's equal to 0 if t is less than 0. If t is between 0 and 1, these two terms will be turned off, but the first term will be turned on, so we have 1/2 t squared. If t is between 1 and 2, then this term will still be turned off, but the first two will now be turned on. So we have the 1/2 t squared from that, and the minus t squared plus t from the second term. And again, that's if t is between 1 and 2. And finally, if t is greater than 2, all three terms are turned on. So we have 1/2 t squared minus t squared plus t plus 1/2 t squared minus t. And now we simplify all of that, and it becomes 0 if t is less than 0, 1/2 t squared if t is between 0 and 1, t minus t squared over 2 if t is between 1 and 2, and 0 if t is greater than 2. which is exactly the same answer that we obtained using the graphical technique. And once again, I find all of this stuff that we had to do in here more tedious than what we did up here for the graphical method. So for this problem, I would prefer the graphical method. But that doesn't mean, and now even for this problem, you may prefer method 2. But certainly the fact that I prefer the graphical method for this problem doesn't mean that I would prefer it for every problem, every convolution problem. So it's great to be aware of both methods of evaluating convolutions. And so that concludes our last daily lecture, and I think that will put you in good shape for doing test 30. So good luck, and I'll see you soon.